If you've ever seen an image like this to describe the probabilities of electron orbitals, you've probably wondered why those probabilities form a ripple around the nucleus instead of a simple gradient.
Well, the answer to this is far more fundamental than you might realize, and was postulated in one of the most important breakthroughs in quantum physics. In the 20th century, 3 incomplete atomic models had come and gone, and the fourth was the Bohr model,
which said that electrons revolve around the nucleus of an atom in quantized orbits at specific energy levels. However, treating electrons only as particles couldn't explain why the orbits didn't decay.
When explaining this in his thesis, a physicist named Louis de Broglie suggested that if photons could act as both a particle and a wave, then theoretically, so could electrons.
He proposed that the electron's wave function forms a standing wave around the nucleus, unlike sitting waves, which my brother does when he wants another drink. To visualize a standing wave, imagine wriggling a slinky with a fixed endpoint. When the wave travels down the slinky, it inverts and bounces back. As long as the period of the wave is an integer multiple of the length of the slinky, you will produce an oscillating wave whose amplitude profile doesn't shift laterally, creating nodes and antinodes.
To create stable standing wave orbitals, the electron orbital circumference must be an integer multiple of the electron's wavelength. From this emerges the idea that if electrons have a specific number of possible energy levels, they have specific wavelengths for which only a certain number of orbital circumferences will be stable.
Schrödinger later redefined these orbitals as regions with a high probability of finding an electron. However, this revolutionary hypothesis that all matter could act as both a particle and a wave had a far more significant impact. It affected our understanding of chemical bonding, lasers, electron microscopy, and even quantum computing.
By changing his assumptions of how our universe could operate, de Broglie taught us a valuable lesson on how science should operate. Because sometimes, to discover something new, you need to approach something old with a different perspective.